I do want to welcome you all to the first ever installment of our Sampling for Forensic Practitioners short course. Your speaker today is Dr. Alicia Carrichieri. Alicia is the director of CSAFE and is the brains behind the operation, bringing you the sampling course today. Alicia, I will turn it over to you.
Fabulous. Okay. Well, thank you. Let's see, I can share my screen, right? Here we are. So thank you very much for joining us. This course, we thought about offering this course because after we started offering the introduction to statistics for forensic practitioners, lots of people said, oh, I wish you talked about sampling a little bit more because I have to do sampling and this and that. And so we thought about putting together this material. Like Anthony said, this is the very, very first time this is offered. And as usual, with time constraints, no forensic practitioner had a chance to review this material. So, you know, it may be widely off target. I hope it isn't. But one thing I would really, really appreciate from you is please send comments back, candid as you wish, in particular about the content, and tell us whether there's important stuff we're missing that is important to you. And for the next time, we'll try to do better. So you guys are our beta testers, and therefore you have a really important job to do. And I count on you. So Joe Zemmels is a doctoral student in statistics, and he's also been with CSAFE quite a while, and he is absolutely fantastic. And as a companion to this course, Joe has put together a practicum. He's going to be recording a couple of videos next week. So after you finish taking the course, you might want to take this practicum. In addition to having examples that he's going to be following step by step, Joe has also written software in Excel that you can use to do various things. And I'll talk about more about that next week. So without further ado, let me start with these statements here. So if you are my age or thereabouts, you probably remember seeing these things. So 84% of women are not satisfied emotionally. That's a lot of women. 70% of all women married 5 or more years are having sex outside of marriage. That's pretty shocking. 95% of women report emotional or psychological harassment. Those statements are pretty stark and, sort of hair-raising. And if you remember, they came out of this book that was written by Shia Haidt in '87. It was called Women and Love, A Cultural Revolution in Progress. And Shia Haidt wrote several other books that had to do with human sexuality. And they were all, page turners and made the news. But it turns out that the conclusions that Haidt was drawing were pretty questionable. So criticisms of the book were many and pretty brutal. Some of them said, conclusions are dubious and of limited value. A colleague of mine that ended up being director of the U.S. Census Bureau said this is the equivalent of medical malpractice in the survey field, and on and on and on. And so the question is, was Shia Haidt wrong? In a way, she enabled all kinds of unhappy women to speak out and tell their story. But the problem was that Shia Haidt made the mistake to generalize all these interesting findings beyond the sample of women that actually responded to her survey. So what is this business of generalizing findings beyond your sample? Well, we will see today that when we sample, what we're doing is we're looking at a subset of the population of interest. And the idea is that from this subset of the population, we would like to be able to say something about the population from which the sample was drawn. In the case of the height participants or respondents, there were several things that should have precluded her from making statements about the population from which the sample was drawn. First of all, the participants, the women that responded to the survey, were all self-selected. This is a real no-no when you want to make inferences about the population, and we'll talk about that later today. There was pretty low response rate. So Shia had talked about the fact that thousands of women responded to her survey, and that may be true, but it turns out that out of 100,000 questionnaires that she sent out, only about 4.5% were returned. And so you can see that unless the sample is absolutely perfect in many regards, making inferences about a population when only 4.5% of the sample has responded is pretty cheeky. And the other thing is that the questionnaires that she sent to all women organizations, such as, the Caucus for Women in here and, the Women's Club of this and so on and so forth. And you have to understand, or one should understand, that the women that participate in those organizations are not necessarily representative of all the women out there. And so think about yourself, for example, how many of these all-women organizations do you belong to? I belong to none of them, for example. And so obviously this particular set of participants were not representative of me or of many other people. So this is a big issue when you end up with a sample that's not representative, is self-selected, has low response rate. And what you find is that you can still compute things from that sample, but the findings apply only to the participants. And you can say really nothing at all about the population from which the sample was drawn. So I offer this as an example because I think this is easy to understand. And what we're going to do today is talk about all these issues and think about how is it that we have to sample in order to avoid all of these issues. All right, so here's an outline for the course. So today I hope to talk about, motivate this business of sampling, give you some terminology and define some concepts. Then we'll talk about the attribute of a good sample, and then this is all kind of short. And then we'll move into sampling methods and what to do with the measurements we take from the sampled items. So that's what we'll hope to cover today. On Tuesday, next week, it'll get a little harder, if you will, because we're going to sort of jump into what's called model-based sampling. And so this is where we're going to talk about the frequentist versus the Bayesian approach. And I know that there's a lot of confusion out there about that. We're going to talk about sample size calculation, which is something that I'm sure some things are going to be new to you, and whatever is left over. And as I mentioned, there's going to be this online practicum that is optional, but I strongly recommend you spend the time. It's going to be about an hour, and it'll be well worth your time. Okay, interrupt if you have questions. There isn't, I think the number of participants is pretty manageable today, so we should be okay. So one more thing that I forgot to say, at the end of the course, we're going to put together a repository, and in that repository, there's going to be the recordings for both sessions, plus Joe's practicum, plus some literature and other materials that you can look at. In particular, we'll post a few of these ASTM standards that are pretty focused on sampling for forensic practitioners. All right, so let's see. So this ASTM 2548, for example, is one of the standards that you probably use in a lab. This is the standard for sampling cis-drags for quantitative and qualitative analysis. And it mentions, for example, statistical sampling and non-statistical sampling. You will probably not be surprised if I tell you that I really don't like non-statistical sampling, but we'll discuss some of it nonetheless. Most of the course is going to be focusing on statistical sampling. And here, if you look at item 4212, this is what I was telling you about. So if you really do want to make inference about the entire seizure, for example, in this particular case, that would be the population, then you have to have a probability sampling approach or a statistical sampling approach. And that's the main topic for today, how to actually do it. All right. So why doesn't this thing move? Did I go too far? Oh, yeah. So let me get, without further ado, get started. So why do we sample? So, there's no such thing as a free lunch. So when you sample, and we'll talk about this in much more detail, when you base your conclusions on a sample, there's always some uncertainty about the results you're getting, mostly because you're not looking at the entire population. And so we sample for different reasons, but in particular, we're going to draw samples from populations because typically there is no hope that we can measure the entire population, or it is too expensive to obtain measurements from the entire population, or really it's pretty efficient if you think in terms of time and effort. It's going to be pretty efficient to work with a sample as long as that sample has been drawn in a principled way. So typically we sample for inferential purposes, and inferential purposes here means learn something about the population from which the sample was drawn. And so there's different types of inference we might want to draw from a population. So for example, we might want to, learn about some attribute of the population. So if I have, let's say, the population of persons in the United States that are of Chinese ancestry, I might want to know what the frequency of certain alleles are in that population. Or maybe I have this huge drug seizure with thousands of baggies containing some white powder, and I would like to know what proportion of those baggies actually contain drugs. Or a different type of purpose is to estimate the association between two variables. So for example, let's suppose I have this fancy instrument and that's super expensive and to get some type of measurements, and it takes forever to get a measurement. And then I have this cheap, fast instrument to get the same type of measurements, but with less precision. So I might try to get a sample and take the measurements with both instruments so that I can calibrate the cheaper instrument using information from the more expensive and accurate one. Or I may be wanting to determine causal effects. For example, if I train latent print examiners in a certain way, does that improve their performance? We are not going to talk about and there's many other issues I might want to work on a sample for. We're going to be focusing on this first bullet, learning something about the population of interest. I cannot stress this enough. The type and the quantity of the data that you collect will determine the type of information you can extract from the sample. So you really need to plan carefully. So there's, choices have consequences. And sometimes you end up with a sample that really is not appropriate to answer the question you wanted to answer in the first place. All right, so what is sampling? So sampling consists in selecting a subset of the items from a population. And here a population can be anything. It can be, let's say, persons, it can be baggies in a container, it can be guns in Chicago, whatever it might be that you're interested in studying. And so the idea here is to draw a subset from that population, analyze the sampled items, and then from that information, say something about the population attributes. And so this I've already mentioned. Why do we sample? Often because it is just too costly or too time consuming to study the entire population. And if the sample that we draw is what we call a random sample or a probability sample or a statistical sample, these are all synonyms, then we can use probability laws to describe how certain we are that the calculations that are based on our sample do reflect the attributes in the population that we're trying to learn about. So there's two major sampling paradigms that we have already mentioned. One of them is probability sampling. And this is items from the population are drawn using some sort of random approach. And that's what we're going to talk about a lot today. And then there's what they call, then there's this thing called non-random sampling. And non-random sampling means I am not using probability at all in order to draw that sampling. And so here's the big picture, and I've already said so. So here's the population about which we want to learn something, and this can be anything. The laws of probability, so I need to know something about this population to be able to draw a sample from it. And so what I use is probability results or probability theory in order to draw the sample. And once I have the sample, what I do is I do statistical analysis or statistical inferences on the sample items to go back and say something about the attributes of the population. So today we're going to talk about both. So we'll talk about the methods that I can use in order to draw the sample. And then we'll talk about what to do once I have these sample items to say something about the population from which the sample was drawn. All right. So learning about the population, unfortunately, surveys are samples too. And unfortunately, surveys have a bad name because there's so many horrible surveys out there. But here would be one of those. But surveys, when well designed, are very valuable as well. And that would include political surveys. And we'll talk about what makes for a good, everything that we say about a sample applies to a survey. What makes a good sample makes a good survey as well. Sorry about the dogs. Okay, so some terminology and definitions. Okay. So a few terms that are going to be used throughout the course. So we've talked already about population. I'll add the word here, relevant population, because not any population is of interest. It's a population I'm interested in. And that's just the collection of items about which I want to say something. And examples could be a large seizure of baggies, for example, containing some suspicious white powder, or the population may be the population of undocumented migrants that avoid detection when entering the US between ports of entry through the southern border. Or it could be the pattern elements of the outsole of shoes, athletic shoes that were worn in Ames, Iowa in the year 2021. Now, these are all different populations. If you think about the first one, that's a pretty well defined population. That's all the baggies you find inside a container, let's say. This is a really difficult population, right? First of all, we don't even know how many people actually make up this population. And if we wanted to sample this population, good luck with that, because this is not a population that wants to be found. So this is a particular, for samplers, this introduces an interesting challenge. And the pattern elements of the outsole of shoes. Yes, in principle, this is something that could be done. I could sample this, but it's kind of hard, right? Because I cannot stop everybody in Ames during the entire year of 2021 and say, let me look at the outsole of your shoe. And sometimes, and so the different sampling methods would be required on all of those three populations. I make this comment that sometimes defining what the relevant population is kind of difficult, but I think for now we're going to leave it there. So sample, the definition is simply a subset of the items in that population. And so from that population, those populations that I mentioned, for example, 100 baggies drawn from that seashore, from that container full of baggies, that would be a sample. In terms of the undocumented migrants, obviously the ones that cross without detection, I won't be able to sample those because I don't know who they are, but I should be able to look at the migrants who were detained while trying to cross one or more times, and use a statistical model, and I might do this on next week, to infer from that model how many may have crossed undetected. And in terms of the shoes, I might, for example, consider placing some maybe scanners throughout locations in Ames where people can walk over, and I would then maybe be able to find out what people are actually wearing in Ames in 2021. In all of these cases, with more or less difficulty, I can certainly draw what would be called a probability sample. But for example, in the case of undocumented migrants, I might consider using something called a non-probability sampling approach. So let me talk first about non-probability sampling, because I really won't say much more about it throughout the course. Non-probability sampling is used extensively in the social sciences and for qualitative research. It's sometimes used in the sciences in very specific situations. And so non-probability samples are useful when designing a random probability sampling scheme is not practical. So for example, when the population of interest is not well defined, let's say you want to know how many teenagers in the United States use illegal drugs. Well, how in the world are you going to find that population and sample them? That's difficult. Or the undocumented people. These are populations that are actively trying to stay out of the way or out of sight. So sampling these is kind of hard. Or sometimes it's the case that you have a very costly to measure variable of interest. For example, you might have the concentration of a radioactive compound at a large site. In that case, you may want, for reasons of risk and cost, and so many other things, you might not be willing to randomly select those sites. The problem is that non-random sampling pretty much precludes making any inferences about the population, and that's a big limitation. So people need to understand that when you do not use random sampling, it's really not correct to say anything that applies beyond the sample you're working with. So there's many different types of non-random sampling methods. Some of the more common ones are what we might call a convenience sample. This is when instead of going out and defining a population, you sample from what's handy to you. So for example, you want to draw a sample of the guns in Chicago. Instead, you go to the armory of the Chicago PD and you sample from there. Or you, for example, have a container full of teddy bears that might be carrying drugs or something. You only look at the ones that are closest to the door of the container. So those would be samples of convenience. And the risk with those samples is that there may be big segments of the population that you're not even giving a chance for inclusion in the sample. There's this thing called snowball or network sampling. This is the following. So you find one or a few members of a population. Let's say I know one or two undocumented migrants in the United States. And I ask them then for their contacts and to build my sample. So that's one way for me to get access to this population that does not want to be found. And so this is useful for, in particular, for this type of populations. And this is one type of sampling that actually can eventually be used for inferences about the population. But the statistical methods that you have to use in order to make inferences about the population when you're working with this type of samples are very sophisticated and subject to, so the errors that you're going to be making are non-negligible. Purposive sample, I tend to call it perverse sampling. I hate to say this. This is when you select items, using some criterion, thinking, for example, let's suppose that you are trying to measure an attribute that is expensive to measure, or something where the risk to subjects may be high. And so in that case, you just pick by hand the items you would like to sample. And an example here is, let's suppose you want to look at pressure-sensitive adhesives, and you want to get the absolutely gold standard measurement using an atomic force microscope. Well, that might take a lifetime, and so you might want to carefully select the type of adhesives you're going to be using to test this measurement technology on. Purposive sampling, I mentioned, for example, that a sample of convenience can be risky because it might result in what we might call a bias sample. And so here's a population, and there's people of many different colors. If you don't include everybody in your sampling frame, so where everybody here has some probability of ending up in the sample, then, and instead just pick the first two rows, let's say, then you end up with a sample that looks like this, and it's clearly not representative of the population because the sample doesn't include any yellow and any orange individuals. Probability sampling, which is where we're going to spend most of the time, this is when we have some random mechanism to select our sample. And the nice thing about probability sampling is that once we're done with it, I can use the laws of probability in order to say something about the population from which the sample was drawn. And so there's any number of methods to draw random samples, but many of them are combinations, are either combinations of three bread and butter methods. One of them is what we call simple random sampling, then stratified sampling, and cluster sampling. And we'll mention a few others, but we'll just go into some depth into these three here. The sampling can be done, so whichever method you use, sampling can occur with or without replacement. And with replacement, as you might imagine, is when I draw an item from the population, I measure whatever it is I want to measure, and then I throw the item back into the population. Without replacement means, and this is what we normally would do, without replacement means I draw an item from the population, I take whatever measurement I want, and then I set that item aside. And then I go and draw a different one from the population. And the reason we distinguish between with and without replacement sampling is that how you do the sampling actually has an impact on how you compute, well, first of all, how you calculate sample sizes, and then how you compute sample quantities. Now, when the population is large, and by large, let's say, I'll throw a number here, but there is no such thing as a definition of large, but let's say 50 to 100 and above, then whether we sample with or without replacement, we assume we're sampling with replacement. And the reason we do that is because the calculations that we all know and love assume sampling with replacement. And so unless you have a very small population, much of what I'm going to say today is, well, actually, much of what I'm going to say today does apply to both, but what I'll say on Friday will typically assume sampling with, next week, typically assume sampling with replacement. Okay, so here's what I'm saying. I don't know why this slide is in the wrong place, but one more time, the main difference between probability and non-probability sampling is the information I can glean from the sample. And in non-probability sampling, I cannot say anything about the population. In fact, sometimes I don't even know the size of the population from which I'm drawing the sample. So here's a simple example, very simple example. Suppose that I'm looking at gun ownership in the state of Iowa. And so there's 99 counties in Iowa. And in this first sampling design, I pick 4 counties purposely. And the reason I pick those 4 counties is because these 4 counties are a nice mixture of urban and rural areas. And then I randomly sample individuals in those 4 counties and ask them about gun ownership. Well, in that case, whatever results I get apply exactly to those 4 counties and nothing else. I cannot say anything about any other county in Iowa, and I certainly cannot say anything about the state itself. If instead I pick 4 counties at random from the 99 counties in Iowa, and then I do the same, so I randomly select individuals and ask them about the gun ownership, then whatever I find out can be generalized to the entire state of Iowa. That's because I randomly selected the counties I was going to be picking, and then within counties, I randomly selected the survey participants. So what this is telling you is that you really need to know how the sample was collected before you can decide whether the results apply to your case or not. So when you're reading the literature and you're not finding how the sample they're using was collected, then you should, well, first of all, shame on the writers, on the authors of the paper. And second of all, you need to wonder whether those results really apply to you or to anything you're doing. Okay, so a little bit more terminology. Inference, we already said this. This is just deriving results about something about the population when I'm using the measurements that I obtained from the sampled items. A sampling frame, this is just the list or the portion of the population items that could end up in the sample. And we distinguish the frame from the population itself because the frame may exclude some population members. So for example, in my survey of gun owners in Iowa, I would not be including people that are institutionalized, like for example, prisoners or people in a psychiatric facility. And so the frame would not correspond to the entire population of those states. It would include, it would maybe just correspond to the free living population in those states. Enumeration is another term you're going to hear, and that just means a listing of each item in the frame. And this is, the gold standard. So you have a population. The first thing you do is you enumerate it. And so in the case of baggies in a seizure, maybe there's 1,000 of those. Enumerating them means just, label them from 1 to 1,000. Coverage has to do with, so coverage has to do with the portion of the population that has a chance of ending in your sample. So for example, if we go back to the sheer height example, the coverage was pathetic, right? Because she wanted to say something about women in the United States, but she only, in her frame, she only had women that belonged to women-only organizations. So the coverage was really not good because she missed every other woman. No other woman had a chance to be asked how they felt about these things. So for example, in the case of the drug seizure, so let's suppose that the container includes some baggies with powder and some baggies with tablets, but I only sample from the ones with powder. My coverage is really not good because I'm missing all the tablets. Strata is just another way to saying subpopulations. And this is when you have a population that's not homogeneous, then you can define strata, and the strata are then homogeneous subsets of that population. And so in the example above, when the seizure includes baggies and tablets, what you would do is you would probably define two strata, the strata with powder and the strata with tablets, and then you would use what we're going to call a stratified sampling design. Here's a very important concept: the idea of sampling error, or sampling uncertainty, or sampling variability. Sampling error doesn't mean that we made a mistake. Sampling error is unavoidable when you are working with a sample instead of with the entire population. So suppose you have a shipment of 10,000 white tablets, and you want to know the average weight of some component of those tablets, some substance in each one of those tablets, and to answer and you have to do some chemical analysis and isolate this particular substance. It's expensive and it's time consuming. If you want a precise answer, you would have to analyze all 10,000 tablets. You don't want to do that. Instead, let's suppose you have a really excellent sampling method and you draw 100 tablets for the analysis. So now you analyze those 100 tablets and you get an average weight of the substance, but that's not exactly, it's not necessarily exactly equal to the average weight of that substance in all 10,000 tablets. And so this average weight has a margin of error. And so the principled thing to do for you is to report the average weight plus minus the margin of error. And the margin of error, we'll say much more in a minute, but the margin of error is something that actually you can control to some extent, mostly via the size of the sample you decide to draw. As you might guess, the larger the sample, the smaller the margin of error. All right. One observation is that sampling is contextual, meaning that the sampling method and the way in which you analyze the measurements that you get from that sample will depend on the question you want to answer. So it's always important to start from a well-formulated question before you even think about how you're going to draw your sample. And a sample that's good in some application may not be good in a different application. And so, again, one has to be careful about what is it that one wants to do with the sample. Okay, so let's jump into what makes a good sample. So what's the attributes of a good sample? So a good sample has the following attributes. It is drawn from the relevant population. It is free from what we call selection bias. It has a known probability of selection. It has a low rate of non-response. And it has what we call low measurement bias. This would be a golden sample. And so what we're going to talk about is strategies about how to draw good samples today. All right, so let me introduce even more terminology, and I promise you this is about to end. So a representative sample is what you think it is. It's a sample that's representative of the population, meaning it reflects the population at least in important ways. It doesn't have to represent the population in every way. It has to represent the population in ways that are correlated with the measurements we're making. So I'll say something more about this later. So the problem with non-representative samples is that they typically result in biased inferences. Selection bias is when occurs when some population items are over or underrepresented in the sample. And a typical case is any study where the participants self-select. So if you look at, so people that participate, for example, this surveys online are absolutely awful because, the only people that participate on those surveys are either the ones that are truly pissed off about whatever it is that is being asked or love whatever it is that is being asked. Everybody else typically does not participate in this type of surveys. The term non-response is used when we fail to obtain measurements from a sampled item. And, for example, one example is I had a sample of size 100. I ran out of time, so I only analyzed the first half of my sample and the other half I ignored. And non-response can be a problem if the missing responses are somehow correlated with the measurement you're taking. So imagine, for example, you have a black box study for firearms examiners, and 200 firearms volunteered to participate in the survey. This is already a problem in the black box study. This is already an issue. But now imagine that only 100 of them return their test kits. Well, the problem there is that you don't know whether the ones that didn't return their test kits were the ones that had problems coming up with their conclusions, and so you don't know whether the ones that returned the test kits were the only ones that knew what was going on, and the other ones that didn't were the ones that didn't have a clue. So that's a real problem. And so we talk about ignorable non-response when the attributes of the items that were not measured are similar to, are not correlated to the value of the measurement itself. So for example, let's suppose that the baggies you did not analyze look identical to the ones you did analyze. So there's no reason to believe there's anything different about them. In this case, the consequences of only analyzing half of the sample and not the other half is that you end up with higher margin of error, and that's about it. But when the non-response is non-ignorable, then you end up with biases in your results. So let's suppose you're looking at the backlog in the analysis of rape kits in crime labs in the United States, and you did this very carefully. So in your sample, you have large, very large, so you have large crime labs in large metropolitan areas and medium-sized crime labs in, medium-sized metropolitan areas and small local labs. And the only responses you get are from the small and medium-sized labs. Well, that's not going to tell you what the true backlog in the analysis of rape kits are, because chances are you're missing, surely it's different. The backlog is different depending on the size of the lab. Here is an example of, this is a wonderful example of non-ignorable non-response. So you get 500 responses, but only 0.2% of them says, no, I hate surveys and I toss them on the bin. And the other ones say, I love surveys. I answer every last one of them. So this conclusion is clearly clearly biased.
Alicia, I'm going to interject here quickly and let you introduce the polls. We have some polls that we'll throw up on the screen for you all to interact with. These first 5 questions are true, false. Are you ready for those to go up, Alicia?
Yes, go for it. In the meantime, there's a question from James that's really an excellent observation. So the baggies might look identical, but not be identical. And this is absolutely true. And I am being a little fast and loose with my examples. A much better approach would be to randomize the testing order than to just take the first half. So let's see what you answered. To generalize, one must not rely on random sampling. That's false, right? So if you rely on random sampling, you should, sorry about the double negative. So in order to say something about the population, to generalize, you have to have a random sample. So most of you guys got it right. Any sample is a subset of some population. That's true. It could be a terrible subset, but it's a subset. If participants in a study are volunteers, findings are likely to be biased. Absolutely true. Most of you got it right. If the sample is large enough, it is representative of the population. Well, this was a trick question, and not really, right? Because I could have a very large sample, but from a population of, let's say, people, and I may only have sample men, and that would not be representative of the population. So sample size is not enough. And finally, non-response can always be ignored. Who cares if we end up with measurements from a small portion of the sample? And I'm happy to report that 98% of you said that's garbage. So congratulations, most everybody did really well. And let's move on. So what's the proportion of items in a shipment? So we've been talking in general, but now we can talk about some specific forensic applications. Questions that you might be asking is, what's the proportion of items in a shipment that meet certain characteristics? So that would be estimating a population proportion. What is the total weight of a shipment? That would be estimating either an average or a total, more or less the same thing. And or the last one is, what is the population size? That is a tough one sometimes, but that might be also a question of interest. And so whatever so this is from ASTM 10521. They say whatever you do, whatever your question is, you a good probability sample, then you can actually calculate things such as biases and variances in an objective way. Okay, this is taking way longer than I thought it was going to take, as usual. So let me skip this because it doesn't say anything new. And this doesn't say much again. So the take-home message here is, even if you don't collect data yourself, you still should be able to critically assess the value or lack of value of data collected by others and in published studies. So, so I hope that what I'll be talking about today is useful to everybody. This is the people that don't rely on data, and look what happened to the dinosaurs, right? All right, so let's finally jump into probability sampling methods. And this is sort of inevitable, but there's going to be some mathematical notation here. So I created this table that you can refer back to. So oftentimes, or most every time, we're going to be using big N to denote the population size. And this, the number of items in the population, and this hopefully will be known, or it'll be, very large, and we won't particularly care exactly what the size is. But so N is the population size. Little n will typically refer to the sample size, so the number of items we sample from the population. And this is determined by you, so you are the master of the sample size. F here is the sampling fraction, so that's just little n divided by big N. How many of the population items are you willing to include in your sample? So these three first terms refer to numbers or sample sizes. The next several ones refer to measurements and estimates. So y sub I here, so y is this generic term for measurements. So this could be the weight of something. It could be 0 or 1 if I'm looking at has the characteristic, doesn't have the characteristic. It could be anything, anything that I am measuring on the sampled items. And we're using this sub I, y sub I, to index the different sample items. So when I talk about the ith sampled unit, this I here can take on values from 1 to little n. So the first sampled unit, the second sampled unit, the last sample unit is the nth one. Y bar here is this is just the average of the measurements in the sample. So this is the sample mean. And we talk about this as a sample statistic. So anything that I compute from the sample observations is called a sample statistic. And the average, and the mu here is the corresponding the mean, the average of the measurements in the population. So mu is unobservable to me unless I take the measurement on every population item. But I don't do that. And so we'll see that the average, the sample mean, is a pretty good guess of the population mean. And we'll talk about how that works in a minute. S here is the standard deviation of the measurements in the sample. And essentially what this S measures is how much each of the measurements deviates from the sample mean. So how far the Y sub i's are from the Y bar. And so when there's a lot of variability in the sampled values, S tends to be large. When all the sample values are sort of clustered, they're all sort of close to the sample mean, then we say that the measurement variability is low. Like the sample mean being an estimate for the population mean, the standard deviation, the sample standard deviation is a good guess for the population standard deviation. And the population standard deviation is often denoted using the Greek for S, which is the letter sigma. So this is the letter sigma. And so these two things go hand in hand, and these two things go hand in hand. And P here stands for proportion. And if what I'm interested in is this variable that can take on the value 1 or 0, so contains drug, doesn't contain drug, is an undocumented migrant, it's not an undocumented migrant. So we talk about sample unit being positive, and it's just positive when it exhibits the quality of interest. And so P is just the number of the proportion of sample units that have this quality. And pi is the corresponding proportion, but now in the population. And again, pi here is just the Greek letter for P. And so the proportion of items in the population is going to be an estimator for the proportion of items in a sample is going to be an estimator for the proportion of items in the population. So let's start with sampling with replacement and be a little bit more precise than what we were today. There's an excellent standard here, the ASTM 1402. We'll make that available to you because it has some pretty good descriptions of different sampling approaches. And so what I say here can be found in that statement too, in that standard too. So sampling, when sampling is done with replacement, here is what happens. I select the first item using some approach. I compute the measurement that I'm interested in, and then I return the item to the population. And so the consequence of this is that each population item can be selected more than once. The next consequence is that the selection probability for any item is the same, regardless of which item was sampled in earlier steps. So if I have, the usual example, an urn with 10 red balls and 10 white balls, half and half, let's say, and I draw the sample and it's a white ball. So the white ball had a 1/2 chance of being selected, right? Because there's half white, there's half white and half black. And so I drop it back. The next white ball has the same probability of selection than the first one had. This is not the typical sampling approach, but it is the one that makes calculations easiest. And so we assume sampling with replacement whenever the population is large when we try to calculate things using the sample. Sampling without replacement, on the other hand, means I select the first item and I measure whatever I'm measuring, and then I set the item aside and go back and select the next item. Now, this has consequences. Well, first of all, each item can be selected only once. And so once you have drawn that item from the population, you cannot draw it again. But the other thing is that after I draw the first item from a population of size n, suddenly I only have n-1 items in the population from which to select item number 2. And so the probability of selection of each population unit depends on how many other units and of which type have already been sampled. In the case of the black balls and the white balls, if the first item I drew is a white ball, now suddenly I only have 4 white balls left in the urn and 9 white balls left in the urine, and 10 black balls. So suddenly, black balls have a higher probability of selection than white balls. And this is what we would normally do. Typically, we sample without replacement. And so, again, when n is large, it really doesn't matter. And so the sample measurements that we obtain, we're going to call y sub 1, y sub 2, y sub n. And from those measurements, we're going to be computing statistics such as the sample mean, the sample standard deviation, the sample proportion of items that have some quality. These sample statistics are called point estimates of the corresponding population quantities, the sample mean, the sample standard deviation, or the population mean, the population standard deviation, or the population proportion. These are the ones that we're interested in. We don't really give one hoot about what this particular sample looks like. We would like to know something about these guys. But in order to say something about these guys, we have to have good point estimates. Okay. So simple random sampling. This is the simplest of all approaches to sample. Essentially, if I have a population of size big N, and I would like to draw little n items from that population, in the case of simple random samples, each item on the population has the same probability of selection. So we'll do an example in a minute, but it turns out that if I have big N items in a population, there's a slew of different samples of size little n that I could draw from that population. In fact, I can compute how many different samples of size little n there are in this particular population, and that is big N to the power of little n. So this gets very large very fast. And so each one of those samples then has a probability equal to 1 over n to the little n of being selected. And this is true when n is large and sampling is done with replacement. But this is true when n is large and sampling is done whether with or without replacement, it doesn't matter, or when n is small and sampling is done with replacement. So let's do a dumb couple of examples when n that are easy to understand. When n is equal to 1, the number of possible different samples I can draw is just n. It's just, each one of the population items could be my sample of size 1. When n is bigger than 1 and the sampling is with replacement, I can compute actually the number of possible samples. Suppose that I have a small population that has 5 items, and the 5 items are labeled A, B, C, D, and E. And I want to draw a sample of size 2. So my samples can be, for example, I could draw A, and then I throw it back, and I get it again. Or I could draw A, throw back, and the next row is B. Or, any number of combinations. And so using that formula that we had in the slide just before, there it's 5 to the 2. And so that tells me there's 25 different possible samples of size 2 I can draw from this population of size 5. And we already said this, in general, it's n to the little n. And so if I have a population of size 100, and I want samples of size 4 with replacement, then it's 100 to the 4. There's 100 million possible samples of size 4 that I could be drawing. So you can see that this goes up very fast. If sampling is without replacement, then what happens in the second row depends on what happened in the first row. So let's suppose that my first draw is B from the same population that I just had. Then the next row can only be A, C, D, or E because B is out of commission. It's already in the sample. And so the possible samples of size 2 that I can draw from that population that we had before, it's now only AB, AC, AD. Remember that BA is the same as AB. And so if you list them out, you'll find that there's 10 possible combinations. So much fewer than the 25 we had before. And so here's the 10 possible combinations. Sorry about the dogs, but I cannot mute myself, can I? Boo! Sorry. There's a formula. Hold on a minute. Booba, shut up. Sorry. And this is how much he listens to me. There's a formula for that. And the form for computing the number of possible samples without replacement of size n. And this is what I have over here. This is read n choose little n. And what that means is take the population size and the factorial of population size, and then divide by factorial of little n times factorial of big N minus little n. For those of you that don't know what factorial is, why would you? Factorial is a fancy name to saying, for example, 5 factorial is just multiply 5 times 4 times 3 times 2 times 1. And so 100 factorial here is multiply 100 times 99 times 98 all the way down to 1. And so if I have a population of size 5 and I want samples of size 2, then the calculation is 5 factorial over 2 factorial times 5 minus 2 factorial, which is what I have over here. And that gives you 10. And so this gives you a general expression to compute the number of different samples. And so if I go back to that population of size 100, sample size 4, then I'm using this expression, I write that down and lots of things sort of cancel out. And so I end up with something that looks like about 4 million. And so 4 million is a whole lot less than 100 million like I had when I looked at samples with replacement, but it's still a whole lot of samples. Okay, so what are the mechanics of simple random sampling? Well, ideally, you have a population that has been enumerated and labeled. So, you know, the labels could be 1, 2, 3, 4, 5. And so if I wish to draw a sample of size little n, 2 things I could do, the 2 most common things I can do is, one is I could use a random number generator from the computer and generate little n values between 1 and 1,000, and I'll draw the baggies or the items that correspond to those randomly drawn numbers. The other one is use something called systematic selection, not to be mistaken with non-random sampling. Systematic selection is as follows. Suppose I want a sample of size n, little n. So I just take big N divided by little n. That's going to be some value k that's much bigger than 1. And what I'll do is I pick a random number between 1 and k. And that's my first item. And then I select every kth item there afterwards. So because the start is random, the rest of the sequence is also random. And so this is also an approach to, James made a really excellent comment in the Q&A. And so please refer to that if you have a minute. I think Joe's answering. So simple random sampling, like the name suggests, is very simple. So you have a population, it's enumerated, so everybody here has a label, and every person has equal probability of selection, and you might end up with a sample like that. So let's see, stratified sampling. This is a method that you would use when the population is not homogeneous. So when you have different types of items in a population, like, for example, shoe brands, and some of those items are more abundant than others in the population, then you might, a more efficient approach to sampling is to first separate the population into strata or stratify, and then collect a random sample from each of the strata. Imagine, for example, that you have one, let's say you have a population of, so you're looking at the pattern of the bottom of the shoes, and you have this one brand that's small, or not too many of those are used in Ames. Well, if you were to pick a simple random sample, unless your sample is very, very large, you might end up without any shoes of that particular brand in the sample. So stratifying then guarantees that even the small groups are going to be represented in the sample, and depends on how you do the selection. It may be the case that the items in the population no longer have the same probability of selection. And so sometimes you have to do something that is called weighting, which is sort of rebalancing the sample so that the representation is of the weighted items is the same as in the population. We don't have time to get into that. But a non-representative sample can become a representative sample if you attach weights to the different sample items. So more notation that we need for stratification. So if you read about stratified sampling, typically the index, the letter H is used to indicate stratum. So if you have a shipment with vials, red tablets, and small white pills, then you would probably define 3 strata. And that means that H can take on values 1, 2, or 3. And N sub H is the population items that are in the H stratum. So the number of, let's say, white pills, for example, or the number of vials. Oh, now. All right. So if N is 100 and if the population is 100 and the sample that I want is of size 10, then the sampling fraction, remember, is 10 over 100. So 0.1 was the right answer and the majority got it right. If sampling is with sampling without replacement means that I can draw the same item more than once. No, because once I draw it, I do not replace it. I do not need to worry about the size of the sample. That really doesn't, that's not correct. The selection probabilities of the first and second items are different. That's correct. And there is no such thing. Okay. So most of you guys, a vast majority got it correct. So that's great. All right. Back to stratified sampling. So once I have defined the strata, then the sampling goes as follows. Perhaps I draw a simple random sample of size little n1 from the first stratum that had big n1 items. And then I draw a simple random sample of size little n2 of from the second stratum that had big N2 items, and so on and so forth. And so if there's big H strata in the population, then the total sample size is just the sum of the sample size from stratum 1 plus from stratum 2 all the way to the sample size from stratum big H. Now, typically, when we think about, we will see this next week, when we think about sample sizes, oftentimes we think in terms of little n, the total sample size, because sometimes we take into account, the resources like cost considerations and say, I can afford to have a sample of, a total sample of no more than 50. And so the question becomes, if I can only have a sample size of 50, how should I allocate those 50 to each one of the different strata? And so there's different approaches to do that. One of them is what's called proportional sampling, or PS, where the sample size from each one of the strata, the strata is proportional to the stratum size. So, for example, if one stratum comprises half of the population, then you might allocate half of the sample to that one stratum. And this is a pretty good approach if all I want to do is estimate the overall population mean, because what happens, or the overall proportion or something about the entire population, because some of the smaller strata may end up with very small population sample representation. So, for example, if one of the strata is 5% of the population, and I use proportional sampling, in a sample of size 50, I would end up with 2 or 3 items from that particular stratum, which is very little. And so, but if I want to estimate the overall population mean, I don't care. Whereas if I am interested in saying something about each one of the strata, so if I also want to estimate the strata, the mean of each one of the stratums, then it is a problem when I have widely different sample sizes from each stratum, because the error associated with each one of those sample means is going to be very different. And so in that case, I may want to draw the same sample size from each one of the strata, regardless of the size of each one of the strata. But that, of course, means now that while I should be able to get very good estimates of the strata means, this sample is no longer representative of the population, because if a stratum comprises half of the population, but the sample from that stratum is only 1/10 of the sample, suddenly I don't have a representative sample. And so we have to be careful about how to compute the population mean if I have this type of allocation. A compromise is to take the n sub h, the sample size from each stratum, to be proportional to size, but only to the square root of the size of each one of the strata sizes. All right, so let's see. So stratified sampling, then first you stratify the population, and in this case we have 4 strata. We have the blue people and the green people and the pink and the red, and then within each one of the strata, you draw randomly. And so you might end up with person 1 from stratum 1 and person 3 from stratum 3, and so on and so forth. Every one of these strata is represented in the sample. Quota sampling is something that you might see. Quota sampling is kind of similar to stratified sampling, but it's used when you only know it's used when you only know the size of each stratum only approximately. But in a sense, it's also a sample of convenience when you do quota sampling. So typically what you do is you have your strata, but then within each strata, you pick purposely. And so this is a problem. It can so you don't pick randomly within each one of the strata. And this can result in huge biases too, in fact. And the famous example is the Dewey versus Truman election. What happened in that case was that this is the Gallup organization. So what Gallup did is they said they had all these interviewers that were going to be asking individuals, who do you intend to vote for? And Gallup said, okay, for the sample, we need this number of women, this number of men, this number of Republicans, this number of Democrats, this number of, old people, this number of young people. And so, but then they let the interviewers select within each one of those strata whomever they wanted to interview. And it turns out that the interviewers didn't do a very good job. And so what happened was that Gallup forecasted that Dewey was going to win by a landslide. And what happened was, and in fact, the Chicago Tribune came up with this. They were so certain that the Chicago Tribune came up with the headline. And at the end of the day, Truman was the one that won by a landslide. All right. Cluster sampling is similar to stratified sampling, but in this case, the population is separated into clusters that do not necessarily have to be homogeneous. And in cluster sampling, what you do is first you sample the cluster. So you don't sample every cluster like you do. So you don't obtain measurements from every cluster like you do in stratified sampling. Instead, you sample clusters first, and then you measure the attribute of interest in every item in the sample clusters. You can also subsample within the clusters, but the idea here is that you don't necessarily select every cluster, but a sample of them. This is commonly used in national population surveys, and for example, typically a cluster here might be a city block or a county, and what you do is you then contact every household in that block. So here is what you do with clusters. So here you have the population. It's divided into 6 non-homogeneous clusters. So then let's suppose that you pick randomly cluster 3 and cluster 6, and you take measurements from every item in those 2 clusters. So that's what you would do. This is the difference. Oh, this is a little funny. So this is the difference between stratified random sampling and cluster sampling. In stratified random sampling, you have for example, you have homogeneous groups, and you obtain samples from every homogeneous stratum in the population. In cluster sampling, you have subpopulations that don't necessarily have to be homogeneous, and you first draw a subpopulation and then take measurements from the items in that particular subpopulation. So when I couldn't think of a good example of cluster sampling, I'm sure there are in forensics, but I thought about this one that may be ridiculous. So suppose you are in the port in LA, and suppose that 30 container ships docked in a week, and you are the inspector, and each container carries about 2,000 containers. Each ship carries about 2,000 containers, and you want to inspect a sample of those containers. So one thing you might do is consider each of the 30 ships a cluster, and then select C of them randomly, and then open every container in those selected ships. Or you can draw a random sample of the containers in each one of those ships. Or you can stratify containers on the ship by, let's say, port of origin, and then randomly sample within those strata. So you can combine any of these methods, and so at the end of the day, so when you so I know what the probability of selection of each container is at the end of the day, because I know how many containers there are, I know how many ships there are, I know what C was, so I know the sampling fraction for the clusters. And then if I do some more sampling within ships, I know what the sampling fraction, for example, might be if I do simple random sampling of containers, or if I stratify them by port of origin, I know how many strata I have and how many containers within each one of those strata I want to sample. So the probability associated with each one container of selection can be calculated if I keep track of all these sampling fractions at each stage. This is stratified sampling and cluster sampling are examples of what's called multi-stage or nested sampling. And as I said here, the trick here is to keep track of the sampling probabilities at each stage, because you're going to need those afterwards in order to make inferences about the population. And we talk about primary sampling units, secondary sampling units, tertiary sampling units, etc. In this example, the SHIP would be, the clusters would be the primary sampling units, and the containers within clusters would be the secondary sampling units. There's any number of other approaches that are more specialized. There's something called area sampling, and area sampling is typically used when what you want to sample is land units. For example, some units in a larger area. And typically to do this, you rely on area photos, satellite images, maps, and you do pretty much the same thing we did here. So I'll give an example in a minute, but you may have this huge plantation, you may have this huge surface full of green plants, and you want to know whether marijuana plants are mixed in with a regular vegetation. In this remote area, you're not going to be walking 100,000 acres looking for marijuana plants. And so what you might do is you might select some random areas on which you're going to be focusing. The bulk of composite sampling is used often for monitoring and surveillance. So what this is although it can be used for example, you get a barrel with some powder and you want to know whether, this powder is, whether this barrel contains something funny or not. You might take several samples from different parts of the barrel and mix them up, and so that you will do only one analysis, one chemical analysis. And so the idea here is to combine materials that is obtained from a group of items into what's called a composite sample and carry out a single analysis. So if you want to detect, for example, the presence of something, this is not a bad way of doing things. This is an approach, for example, that's used by natural resources people if they want to look at the concentration of, something in a lake. They oftentimes will take a bunch of samples of water from different depths and different part of the lake, mix them all up, and then see whether that toxin or whatever is present or not. If it's not present, you're golden. If it's present, then you might have to do something a little bit more specific. A recent example of this type of sampling is with COVID. And so some colleges, some universities have been doing early detection of COVID on college campuses by looking at the wastewater that comes out of dorms. And so if there's no COVID in the wastewater, you'd think that every student that lives in that dorm is healthy. If you detect the virus in the wastewater, then you have to go and figure out which one of the students has COVID. This is different examples of area sampling. So you could, for example, pick points in an area randomly, or you can pick systematically, or you can pick in some sort of stratified pattern if you have two different distinguishable types of area, like the orange and the yellow. Or you could do what's called transect sampling. So you just draw lines and then collect samples along each one of these lines. This is where you do this randomly. And you see you're mostly missing this particular stratum. This is where you stratify. This is where you do it systematically. Or you might define, square, some bigger areas called quadrats, and again, randomly stratified systematically. And depends on so how do you decide between any one of these things? Well, you have to know about the area you're sampling. because you have to know, for example, that there's two different types of, let's say, soil that you have to worry about. And you have to know where one soil ends and the other one starts. And so the type of sampling you do and how you collect the sample really requires that you understand the attributes of the population from which you're going to be sampling. So what comes next? One more test your knowledge thing. So let's see, stratified sampling is appropriate when the population is composed of several homogeneous groups. That's correct. A cluster is the same as a stratum, except that the term comes from ancient Aramaic. That's not true. Quota sampling, so remember a cluster is sort of similar to a stratum, except that a cluster doesn't have to be homogeneous. Quota sampling is the best method to avoid bias. That's not true. In fact, that's a pretty darn good way to ensure you're going to have a biased sample. And the term primary sampling unit refers to the VIPs in the sample. Not really. It refers to the first stage units that I sample. All right, thank you guys. So I have about, 10 minutes? Yeah, I am going to continue going as far as I can, but I am not finishing today. So much of the rest of the slides we're going to move to next week. So what comes next is inference. So you have now drawn a sample from the relevant population. You're pretty comfortable with your sample. You have your N sampled items. And the next step is to use those items to make inferences about the population. And so by inference, I've already said this, we mean let's make an educated guess about the population attribute of interest. For example, the proportion of baggies that contain cocaine in the seizure, or the average dollar value, mu, of each illegal transaction stored in a survey. This might be for a forensic audit, or the number of firearms in a contraband shipment that includes 5,000 crates. And so these are all inferential questions, and how we go about answering those questions is going to depend a little bit on how we went about drawing our sample. So, all right. So this is the next part of the course. And again, so we talked about this piece, and now we're going to be talking about going back from information gleaned from the sample to saying something about the population. So what kinds of inference can we make? So we're going to talk about getting point estimates and interval estimates for population quantities. And to talk about this, I'm going to focus on two population quantities that we're going to be making inferences about. One is the population proportion pi of items that have some sort of quality. And another one is the population mean mu of some substance, the weight of something or the dollar value of something along those lines. So when N is large and we use simple random sampling, this is familiar territory for most of us because this is what you learn in Stat 101. Sample mean is an unbiased estimator of the population mean. The sample proportion is an unbiased estimator of the population proportion, and so on. When the population is finite, meaning it's relatively small, whatever we do, we always have to use this thing called a finite population correction factor. And we'll call that FPC, and we'll see what that is in a second. And when sampling is multi-stage, then the estimators have to account for the sampling design and for the probability of selection at each stage, because otherwise the sample estimates are not going to be good guesses for the population attributes of interest. So let's start with inference for the population proportion from a simple random sample. So this is pretty easy. So let's suppose I want to estimate I have a large population and I want to know what is the proportion of the population items that exhibit a certain property. I'm going to call those positives. So a point estimator that has very good statistical properties is simply P. The sample proportion, or the number of items in the sample that actually exhibit the attribute. So if I have 100 tablets in my population, and let's suppose that unbeknownst to us, 40% of those tablets are positive. And we draw a sample of size 10 from that population, find that half of them are positive. My guess for pi, so this is the actual pi, is going to be 0.5. And so, or 50%. So in general, unless we are insanely lucky, the actual sample estimate, P, is not going to be exactly equal to the value it is trying to estimate, the unobservable population value. So the question is, how close can we hope P is going to be to pi? We know it's not going to be the same, but how close can we hope it to be? And this is where it is important to have a probability sample, because without probability calculations, I will not be able to say anything about how good P, my sample estimate P, is. And so give me the 2-minute warning, Anthony, if you don't mind, which is in like 2 minutes. And so I'm going to introduce this idea of your point estimate. In this case, the variability of P. So this has to do with that idea of sample uncertainty or sampling error that we just defined earlier today. Remember we said if I have a sample, a population of size n, there's any number of different samples that I could draw from that population. And so each one of those samples, let's suppose I draw 100 samples from the population, and for each one of those, I compute P. Well, each one of those P's is an estimate of the true population proportion pi, but they're going to be all different from each other because those P's are going to depend on the sampled items. And so the question is, how close can I expect each one of those P's to be to pi? And in order to quantify that, I have to compute something called the standard error of the estimator. And the standard error of the estimator simply tells me how close I can hope to be from pi. And so here's a little, 2 minutes, perfect. So here's a little example. I have a this is the population I was describing. We have 100 tablets. 40% of them, or the dark blue tablets, are bad news. The light blue tablets are just decoys. And so the true pi here, of course, I don't know that, is 0.4. I draw random samples of size 10, and these are actually random samples that I drew from here. And in the first one, I get 5 positives and 5 negatives. In the second one, I get 3 positives and 7 negatives, and so on and so forth. Typically, I will only draw one of these, but in the abstract, the variability across, between all those point estimates is measured by the standard error of the estimate. In the specific case of the population proportion, the standard error is computed like we have over here. So it's the estimate itself times 1 minus the estimate itself divided by n, square root of all the stuff, times this finite population correction. And the finite population correction is simply this over here. So population size minus sample size divided by population size minus 1, square root of 1. So for n large, this entire thing goes to 1 or approximates 1. And so multiplying by 1 is like doing nothing. And so for large n, I can ignore this finite population correction. And that's what we normally do in Statistics 101. But if we want to be careful, or if we know we have a finite population where n is not too large, then we should be using this finite population correction. And so I am going to quit here, and I am going to pick it up from the variability of P when we start again next Thursday.
Thank you all for joining us, and we hope you have a great day.